Hi Level 3s and welcome back to 3.6 Aqueous Chemistry. This is Lesson 3 Part A. So our learning objectives today are to describe how pressure affects equilibrium, how temperature affects equilibrium, and how catalysts affect equilibrium, and then we're going to look at equilibrium graphs. The first three learning objectives are just a recap from Level 2, and this one's new down the bottom about the equilibrium graphs. Okay, so the first, here's a do now, so I'll just get you to pause and give this a go. So I'm now going to go through the answers. So it says write KCs for the following. So KC equals products divided by reactants. You can only include gases and aqueous in your KCs, so don't make any mistakes there. So there's water's a liquid, so we don't include it. So the second KC is going to be CO to the power of 2, because it's got a 2 here, divided by CO2, and we ignore this because it's a solid. Okay, hopefully that makes sense. What are the zinc complex ions? Okay, so the zinc complex ions are going to be, okay, oops, that should be 2 minus. Perfect. Oh, sorry. And what's happening in this graph? Okay. Describe the before and after concentrations. So if you look here, what I'm trying to get at here is this reaction here is saying that you start with no product, because this reaction is 3H2 gas plus N2 gas goes to 2NH3, so this is the Haber process. So this is the product. So you start with no product, you're starting with reactants. As the reaction proceeds, the reactants decrease in concentration as the products increase in concentration, and that's because the reactants are being used to make the products. And then equilibrium is established when the concentrations do not change. Okay, so when the concentrations do not change, you end up having, you end up at equilibrium. Okay, so I hope that makes sense. So the first change that we're going to talk about is a recap from Level 2. So what happens if we change the pressure of an equilibrium? Now, to change the pressure, you have to change the volume, and these are an inverse relationship, which means to increase the pressure, you have to decrease the volume, and to decrease the pressure, you increase the volume. Okay, so only gases are ever affected by pressure changes. That's really important. So if you've got an equilibrium involving solids, liquids, or aqueous solutions, they're not going to be affected by pressure. It's just going to be gases. So if we look here, this is what I was talking about. So here is a volume of space, and if we compress it, then the pressure has been increased. Okay, now really interestingly, we know the definition of concentration is the number of particles in a given volume. Okay, in a given volume. So that's the definition of concentration. So if we've got this many particles, let's just count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you've got 10 particles here, and let's count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 particles here. So the same number of particles, but you'll see here, this volume is 2 litres and this volume is 1 litre. So actually, if we change the pressure by decreasing the volume here, what we've effectively done is increase the concentration, because here we've got 10 particles in 2 litres, which say let's say here they've put 2 moles. So if it was 2 moles over 2 litres, that's 1 mole per litre. And here you've still got the 2 moles, but now you've only got 1 litre, which would equal 2 moles per litre. So really pressure changes are actually just concentration changes. So that's just an interesting tidbit to keep in mind. Okay. Yeah. Okay, so if we change the pressure by increasing or decreasing the volume, we need to talk about how the equilibrium will respond. Now remember, with equilibrium changes, you always must say the direct opposite. Okay, so if we increase the pressure, then the equilibrium will shift to decrease the pressure. I always state the direct opposite straight away. How will the equilibrium decrease the pressure? It'll do it by moving to the side with the least number of gas moles, the least number of gas moles. Now you'll see I've bolded gas moles, and that's because if you don't use the word gas moles, you will not receive any marks for this question, because you've got to specify that it's only gases that are affected. So what if the pressure is decreased? Then the equilibrium will shift to increase the pressure. I say the direct opposite first of all. It'll shift to the side this time with the most number of gas moles. Okay. Now what if both sides of the equation have the same number of moles? Well, then nothing happens. Okay, so nothing happens. And remember, the only thing that changes Kc is temperature, so Kc will not change. Kc will not change. Just like concentration, Kc doesn't change. So let's have a look at this equilibrium. Okay, it says if the pressure is increased. So if the pressure is increased, our equilibrium is going to shift to decrease the pressure. Okay, always does the direct opposite. How will it decrease the pressure? It's going to decrease the pressure by moving to the side with the least gas moles. You've got to say gas moles. Okay, now here we've got 2 gas moles on the products. Okay, and 1 gas mole on the reactant. Okay, so therefore equilibrium will move to the left, or the reactants. Okay, and so you'll get more of this. So I hope that makes sense. So if the pressure is increased, the equilibrium will shift to decrease the pressure. It'll do this by moving to the side with the least gas moles. The products have 2 gas moles, the reactants only have 1 gas mole. So therefore the equilibrium will shift to the left because there's 1 gas mole, and that'll alleviate the pressure. And I have put this all here. Oops. So let's do the next one. So what if the pressure of the system is decreased? So if the pressure of the system is decreased, the equilibrium will shift to increase the pressure. How will it increase the pressure? The equilibrium will shift to the side with the most gas moles. Okay, you can't forget to say gas moles. Okay, so the products have got 2 gas moles. 2. The reactants have 3 plus 1 makes 4 gas moles. Okay, so therefore the equilibrium will shift to the left, okay, because it's got the most gas moles. So I hope that makes sense. And there's the answer there. Okay, changes to temperature. I'm just going quite quickly through this stuff just as an FYI because this is level 2, so this is stuff that you should already know. So an increase in temperature or a decrease in temperature, they always do the same thing. So we've got to remember there are 2 types of equations in chemistry that involve heat. You've got an exothermic reaction, and an exothermic reaction releases heat energy to the surroundings. Okay, and you've also got an endothermic reaction, and an endothermic reaction absorbs heat energy from the surroundings. Okay, so exothermic surroundings get hotter and endothermic surroundings get colder. Now, you all know all this from previous year's chemistry, so these are kind of, what happens here is always the same. If you increase the temperature of a system, so if you increase the temperature, the equilibrium will shift to decrease the temperature. There's only one way to decrease temperature, and that's to move in the endothermic direction, and that's because this absorbs heat. So that's a stock standard. So whenever temperature goes up, this happens, okay? So I'll say it again. So if temperature is increased, the equilibrium will shift to decrease the temperature. It'll do that by moving in the endothermic direction because endothermic reactions absorb heat energy and equilibrium will be re-established. So the opposite happens with a decrease in temperature. So if the temperature is decreased, the equilibrium will shift to increase the temperature. It'll do this by moving in the exothermic reaction direction, which releases heat energy. Okay, releases heat energy. So if heat energy is being released, it's in the exothermic direction. So these 2 are always the same, and this is a key thing here. Kc does change with temperature, and that's because one of these reactions is it's not actually in balance. It's completely favoured over the others. We don't go into too much detail as to why that is. It's actually to do with rate constants and the rate side of things, and that's something that we don't actually cover with level 3. So you just need to know for level 3 that the only thing that it changes equilibrium constants is actually temperature. Okay, otherwise nothing change. The Kc won't change. So just a recap of what exothermic and endothermic reactions are. So endothermic reactions, more energy is absorbed breaking the bonds in the reactants than is released when making the bonds in the products, or alternatively it's bond breaking, okay, and surroundings get colder. exothermic, more energy is released in making the bonds in the products than is taken in to break the bonds in the reactants, or it can be described as bond making, and surroundings get hotter. I'm not going to harp on too much about this stuff because I think you guys all know that from level 2. If you are struggling, you could search up on my YouTube channel the level 2 lessons on endothermic, exothermic, and that goes through these in much more detail. Just a wee tidbit again that exothermic reactions are far more common, and there's 2 reasons. This hump here is also known as the activation energy, which is the energy needed to start a reaction. And you can see here for an exothermic reaction, the activation energy is far, far smaller. So it takes less energy to start the reaction, so naturally that means it's going to occur more often. And the other thing is that this scale here is actually potential energy, not just energy, potential energy. And so potential energy is what's stored in the bonds. Now you'll see here that the products of an exothermic reaction have a lower potential energy. And that means that these bonds are actually stronger and that these products are actually more stable. Anything that's got a lower energy is more stable, okay, and it's more stable because the bonds are far stronger and they're less likely to break, okay, and that's why they've got a low potential energy, because they're not likely to break. Whereas so your products of your endothermic reaction have a much higher potential energy. The bonds are weaker, they're more likely to break, which is why they've got a higher potential energy, and they're less stable. So there's 2 reasons why exothermic reactions are far more common and why you see far more examples of this. So the first reason is that the activation energy, the hump is way smaller, so less energy is needed to start exothermic reactions. And the second reason is that the products produced are far more stable because they've got lower potential energy, so stronger bonds. So just another recap, if a reaction is exothermic in one direction, then it's endothermic in the other. So this is the Haber process. So making ammonia is exothermic and the breaking up of ammonia to N2 and H2 is endothermic. Okay, so here's an example here, and you can see that this reaction is endothermic. When you read a reaction like this, this means the forwards reaction is endothermic. So if the forwards reaction is endothermic, then the reverse reaction is exo. Okay, so forward is endo, reverse is exo. Okay, so what happens if the temperature of this system is increased? So if we increase the temperature, remember the equilibrium will do the direct opposite. So the equilibrium will shift to decrease the temperature. And how will it decrease the temperature? It'll shift in the endothermic direction, and in this case that means the right, and it'll do this because this will absorb the added heat energy. Okay, so just go through that one more time. If the temperature's increased, the equilibrium will shift to do the direct opposite, so it'll shift to decrease the temperature. It'll do this by moving in the endothermic direction, which happens to be the right hand side, because the endothermic direction will absorb the added heat energy. So let's do the opposite then. What happens if the temperature of the system is decreased? If the temperature is decreased, the equilibrium will shift to increase the temperature. How will it do that? It'll do that by moving in the exothermic direction, which happens to be the left-hand side. Why? Because the exothermic direction will release heat energy and restore equilibrium. So I hope that makes sense. So why does Kc change when temperature changes? It causes one whole reaction to be favoured over the others, and as if we're favouring one over the other, then you'll get a massive disproportion of products over reactants, and mathematically that changes Kc. There's actually a lot to this stuff, and it involves rate constants that we don't go into, so all you need to remember right now is temp is the only thing that can change Kc. Temp is the only thing that can change Kc. Okay, so I'm going to pause the video here and I'll come back for a part B and we'll do some examples, and then we're nearly done for this lesson, recapping the level 2 stuff.